Yeah. Good evening, students. The today's class we'll see about Sommerfield's atomic model. As we have yesterday, we have seen about the Bohr's atomic model, and we have seen some drawbacks, whatever we have in the case of the Bohr's atomic model. Now, today we'll start Sommerfield theory. So, why it has been means what is the assumptions made in the Sommerfield's theory, and how the drawbacks whichever we have in the case of Bohr's atomic model has been solved. That we'll see here today. So just wait, this screening 1 minute. One minute screen share. Just wait 1 minute because some disturbance is there. One minute. Wait a while. It's whiteboard is coming. I'll write and here and I'll show you all this. So I'm able to write 1 minute. Right. Okay. So now we'll start this new theory, that is Sommerfield atomic model. We can say that Sommerfield atomic model. We'll see about the Sommerfield atomic model. So why we have got this Sommerfield atomic model is in order to overcome the drawbacks of Bohr's atomic model, scientist Sommerfield in the year 1921, modified Bohr's model by introducing the new idea or new concept, which we call it as a elliptical orbits. So, and he says that according to the Sommerfield, he says that motion of the electrons in elliptical orbits and taking into consideration the variation of mass with the velocity. So he introduced a new idea of motion of electron in elliptical orbits. So the new concept that is elliptical orbitals. Okay, elliptical orbits. So by taking this motion of electron in elliptical orbits and taking into consideration the variation of mass with velocity. So another concept what he has taken is variation of mass with the velocity. So by taking these two into consideration, that is elliptical orbital concepts and variation of mass with a velocity, that is the motion of electron in elliptical orbits, and taking the consideration the variation of mass with velocity. So he has been overcome whatever may be the drawbacks which we have in the case of what we call Bohr's atomic model. He has been overcome, and he proved experimentally whatever the things he has been assumed. Okay, so first we'll move into the concept of elliptical orbits. So first we'll move to the concept of elliptical orbits. Elliptical orbits. Okay, so what is elliptical orbit? What he says, what he has been explained, that we'll see it now. Then we'll move to the uh, allowed elliptical orbits, and all those thing concepts will move here. Okay, so first, if you take the elliptical orbital concept, according to the Sommerfeld, the electron moving around the nucleus under the inverse square force like planets around the sun. Okay, so what he says is that is according to the Sommerfeld, the electrons which are moving around the nucleus under the inverse square force. Okay, and he compared with like a planet around the sun. He has been compared. Okay, so according to him, so if we draw elliptical orbital concept, so we know that the shape of ellipse will be like this. Okay, the shape of the ellipse be like this. So in this case, the radius is not constant from the center, but it is having the major axis as well as the minor axis you are going to be have here. Okay, so in addition to the circular orbits which are given by the Bohr's, he suggested that instead of circular orbits, this what we call elliptical orbit is has been taken into consideration here. Okay, so in the elliptical orbits, the position of the electron at any time may be fixed by two coordinates. Okay, at any time by fixed by two coordinates. What are those coordinates? Means you can say that r and phi. Okay, at any time if you want to know the motion of the electron, it is fixed by two coordinates like r and phi here. So r is nothing but suppose here if it is the nucleus is at this point if you are having. Okay, so electron is revolving around this one in this elliptical orbit. So at this point, okay, at this point, the distance from the nucleus to the electron is this is the electron if you consider, this is the nucleus if you are having at this point, then r is the what we call radius at that particular point, and phi is nothing but the angle between these. Okay, this is what we have the phi here. Okay, so r is the radius vector, and phi is the angle which the radius vector making with the what we call major axis of the ellipse. So if you draw in this manner, suppose like this, you are going to be have. Suppose this is the point where electron is there. This is the nucleus if you are having. So this one we call it as a radius vector, and the angle here it is phi we are going to be called here. R is nothing but the radius vector, and phi is the angle which the radius vector makes what we call with the major axis of the ellipse. That is, we call it as a phi as a azimuthal angle we are going to be called. Okay. Now here, we will consider an electron of mass m. Okay. So if we will consider here electron which is having the mass of m it is having. So this electron with mass m, and what we call it is moving with velocity. So here it is, instead of velocity, we will be calling it as a tangential linear velocity. We will be calling it as what? Tangential velocity we are going to be calling. Instead of linear velocity, we will be calling it as a tangential velocity here, because it is going to be changes every time. So we'll be calling it as a tangential velocity. So we have considered an electron of mass m and which is moving with a linear tangential velocity v, which is revolving in the elliptical orbit. Okay, so the tangential velocity of the electron can be resolved into two components. This tangential velocity can be resolved into two components. So here the one component, the first component, that is a one component is one along one along radius vector. One is along the radius vector, so which we'll be calling it as a radial velocity. So we'll be calling it as what? Radial velocity we are going to call. And other perpendicular to the radius vector, which we'll be calling it as a transverse velocity. So we'll be calling it as what? Transverse velocity we are going to be calling. Okay. So we'll be calling it as a one is a radial velocity, and another one is a transverse velocity, because tangential velocity is resolved into two components. One is the transverse velocity, another one is the radial velocity. So corresponding to these velocities, the electron has two momentum, one along the radius vector, which will be calling it as a corresponding the radial velocity. The momentum whichever we are going to be have is called as a what we call a radial momentum we are going to be called. Okay, radial momentum. And along this what we call another perpendicular to the radius vector, which is known as a azimuthal momentum we are going to be called. Due to the transverse velocity, we'll be calling it as what? Azimuthal momentum we are going to become. So as we know, the tangential velocity has been we're taking it two components. One is along the radial velocity and another one is along the transverse velocity, and corresponding of these velocities, the electron has two movements, one along the radius vector, which is called it as a radial momentum, and other perpendicular to the radius vector, which is known as azimuthal momentum we are going to be called. Right. So now after this, when the electron is moving in the what we call elliptical orbits, in order to quantize the elliptical orbits, okay, in order to quantize the elliptical orbits, Sommerfeld introduced two quantum numbers. Okay, Sommerfeld introduced two quantum numbers. One is nr we are calling. One is nr, and another one which we calling it as a n5 we will be calling. Okay, so Sommerfeld introduced two quantized elliptical orbits. One is one we will be calling it as what nr, and another one we will be calling it as a n5. These are the two quantum numbers which has been introduced by Sommerfeld, and because they stands for one is periodic system, so therefore we can call it as a periodic system. Hence, we'll be calling it as a nr plus n5 should equals to n into, that is n dot nr we are going to call, which is known as a radial quantum number, and n5 is angular or azimuthal quantum number, and this is known as what principal quantum number. N is a principal quantum number we have. So this is the two quantum numbers which has been introduced by this what we call Sommerfeld, right? So on the basis of the classical mechanics, otherwise classical dynamics, it can be shown that the length of the semi-major axis determined by the principal quantum number n, while the length of the semi-minor axis depend upon the azimuthal quantum number n5. Okay, so for the normal states, so I'll go to the next page. So for the normal states, right. So as I told that on the basis of the classical mechanics or classical dynamics, it can be shown that the length of the semi-major axis determined solely by the principal quantum number n. So while length of the semi-minor axis depends upon the azimuthal quantum number. So for the normal state of the hydrogen atom if we take, the principal quantum number n is equals to 1 we have, and corresponding to n is equals to 1, there are two possibilities. That is, n, if you want to get n is equals to 1, we have two possibilities. Either nr is equals to 0, comma n phi is equals to 1, because nr plus n phi is equals to n we have. Okay, nr plus n phi is equals to n we have. So either we can take nr is equals to 0 or n phi is equals to 0. Why? Because if you want, we know that we can write here, since what we have, n is equals to nr plus n phi. That is, the principal quantum number is a combination of these two. So nr is equals to 0, n phi should be 1. This is the one condition we are going to get. And another condition which we can write, it is nr is equals to 1 we can write, and n phi we can write it as what? 0 we can write. So if you write nr is equals to 1, n phi is equals to 0 if you write, so automatically what will happen here is n value is going to be 1 you are going to get, because nr is equals to 1 plus 0, so n is equals to 1 you are going to get. So in this case also n value becomes 1 here. So this is one condition you can have, otherwise this is another condition. So these two may be possible, either nr is equals to 0 or nr is equals to 1 we are going to be have. So now the first condition whichever we have taken, like in this case, what we have considered here, n phi is equals to 1. And in the second case, what we have considered, n phi is equals to 0 we have considered. So in this case, when n phi is equals to 0, that is, n phi is nothing but the semi minor axis is 0. Okay, n phi is nothing but semi minor axis is 0. So in this case, the elliptical orbit, whichever we have, that elliptical orbit is converted into a single line, and the electrons have to pass through the nucleus twice during the every period. Okay, twice during the every period. So this type of motion is not possible. So this type of motion is not possible. Hence, n phi may not be 0. So these are the two conditions we can see here. N, it has to be 1. The principal quantum number should be 1, means either this condition, that is first condition what we have. This is the first condition, nr is equals to 0, and this is the second condition in which nr is equals to 1. So nr is equals to 1 means n phi is equals to 0. So this condition may not be possible. This condition may not be possible. Why it is not possible means it will be a straight line you are going to be have. Why? Because n phi is equals to 0. This is a semi major axis only you are going to be exist. This semi minor axis does not exist. So like this, only simply a straight line you are going to be get. In this straight line, the electron has to be moved from here to here and here to here. So this condition is, that is the reason why this condition is not possible. Okay. So the second condition, whichever we have taken, so this is not possible. Okay. Now, if you take the another condition, what we have is n phi value should be equals to 1. Okay. N phi value is equals to 1. So in this case, what we are going to get, n is equals to 1 we are going to get. So if n phi is 1 and the first orbit is a circle, so what is that we have? N phi is equals to 1. So in this case, what will happen means only this you are going to get. So this is the radius you are going to get. So therefore, you are going to get this circular orbit you are going to get. So the circular orbit, sorry, this is the from the center if you take. So this is the circular orbit. So as we have seen in the case of the Bohr's theory, so he says that at the center we will be having the nucleus. This is the center nucleus we are going to be have. And these electrons, whichever we have, they are going to be revolve around the nucleus in this manner you are going to get. So in the case of the condition, when we take n phi is equals to 1, we are going to get this condition you are going to get. So this is in the case of the n is equals to 1. And if you have n value is equals to 2 here, okay, n value is equals to 2. That is nothing but the principal quantum number value is equals to 2 if you want to get. So therefore, actually what we said, n is equals to the combination of both these nr and n phi you are going to be get. So in this case, what will happens means, if you take n is equals to 2, so the n phi value, okay, the n phi value may be possible, it may be equals to either 1 or 2 here. So if n phi is equals to 1, nr value is equals to 1. If n phi is equals to 2, nr value should be equals to 0. So these are the two possibilities of n phi we are going to be have. So corresponding to n is equals to 2. So in this case, two orbits are possible. One is n is equals to 2 here. One is n is equals to 2 here. In this case, n5 value may be 2 here you are going to be have. Okay. So in this case, if n5 value is equals to 2, again, the what we call the electron should be revolve around the nucleus in circular orbit. It has to be revolved. So because n5 is equals to 2 means nr value is equals to 0 automatically. So this is you are going to be happen. Next condition, next condition, in order to get n is equals to 2, what we have is n is equals to 2, either nr value is equals to 1 and n5 value is equals to 1 we are going to be have. Understand? In this case of n is equals to 2, nr value is equals to 1 and as well as the n5 is equals to 1. In this case, you are going to get what we call ellipse you are going to get. So in this manner, ellipse you are going to be get here. So for the quantum number in which n is equals to 2, the two possibilities whichever we have is means two orbits are possible. One n is equals to 2 in which n5 is equals to 2. This is the condition which we have taken. So for this you are going to get this circular shape you are going to get. Otherwise, in case of n is equals to 2, n5 is equals to 1 and nr is equals to 1. So in this case, we are going to get ellipse. That means when we have taken here, so the first condition, when n is equals to 1, only circular orbit you are going to get. Circular orbit you are going to get. This is not possible. And when we have taken n is equals to 2, either you may be getting one condition is circular orbit you are going to get, another condition is elliptical orbit you are going to get in this manner. Okay. So this is one condition you are going to have. So like this, depending upon the n value, the orbits, whichever we are going to get is what we call either ellipse or these what we call circular orbits you are going to get. Okay. So next, Sommerfeld assumed that the same generalized condition which has been postulated for circular orbit also holds in case of the elliptical orbits. That means this integration of PR dr is equals to nrh we have. Okay, nrh we have one thing, and integration of p phi d phi is equals to n phi h we have. So this is one you have, and this is the another condition we have. So for a circular orbit also holds in case of the elliptical orbits we are going to be have. Here we have written PR and P phi. So these PR and P phi are nothing but the components of linear momentum of P of the electron along the radial direction. PR is nothing but along the radial direction, and P phi is nothing but along the transverse direction respectively. And moreover, we have NR and N phi. These NR and N phi are nothing but the integers, like n is equals to 1, 2, 3, whatever you are going to be have. So more specifically, if you say NR is nothing but it is a radial quantum number, and N phi is nothing but the angular azimuthal quantum number. So in this way, he says that the what we call Sommerfeld says that electrons are revolving around the nucleus instead of circular orbits. It is going to be revolved in the form of what we call elliptical orbits. He says that. Okay. And if you see, these all possibilities we are going to be have depending upon the NR and N5 values, like semi-major axis and semi-minor axis values, you are going to be get different types of elliptical orbits. But he says that among that only some of the orbits, that is elliptical orbits, are allowed. The remaining may not be allowed here. So what are those allowed elliptical orbits? Here we'll see here. Okay, allowed elliptical orbits. All the orbits are elliptical orbits are not allowed whenever the electron is revolving around the nucleus. Okay, so certain orbitals are only allowed here. Okay, so here how we have to what we call how we derive this allowed elliptical orbits is so from the classical mechanics, if you see, it is known that the angular momentum, so which we have called it here, it is a p phi. The angular momentum is p phi we have called. So according to this classical mechanics, it is known that the angular momentum is phi, remains this p phi angular momentum remains constant here. Okay, remains constant during the motion of the electron. So therefore, here the equation, whichever we have taken equation 2 here. So this, if you take integration, if it is revolving toward 360 degrees, like integration from 0 to 2 pi, p phi d phi, which will be equals to, as we have taken that according to the classical mechanics, p phi is constant. We can take outside this p phi of integration 0 to 2 pi d phi we are going to be have. Okay. So if you solve this one, we getting it as a p phi, and integration of d phi is phi. Integration of d phi is phi. And moreover, if you substitute the limits from 0 to 2 pi, so this value we are going to get it as a p phi. Okay, p phi into 2 pi you are going to get. So upper limit is 2 pi and lower limit is 0. So therefore, we are going to get it as a p phi into 2 phi you are going to get here. So which is equals to, actually, this will be equals to n phi h here. Okay, so p phi, what we have got? P phi 2 pi is equals to n phi h we have. So therefore, if you want to know the p phi, which is constant, p phi is equals to this n phi into h by 2 pi we are going to be have. N pi by n pi h by 2 pi. So this is third equation which we have. So in an elliptical orbit, the radius vector is a variable quantity. The radius vector is a variable quantity. P phi is constant, it's okay. But in the case of the elliptical orbit, radius vector is variable quantity. A radius vector is a variable quantity. It is a variable quantity here. Radius vector is always variable quantity. So therefore, we have the equation like what we have here. Corresponding to the radius vector, we have integration PR dr is equals to nr h we have. PR dr is equals to integration of PR dr is equals to nr h we have. Now we'll take this. Next we'll move into this here. Right. So here, as in the previous one, we have here, what we have is integration of PR dr is equals to nrh we have. So therefore, now we'll consider the value of PR. Okay. So considering the value of PR, right? So what we have, PR is equals to m into dr by dt. Can write PR is equals to m into dr by dt here. So now what I'll do is m into, I'll write this as a dr by d phi into d phi by dt we can write here. Okay, just we are multiplying and dividing with the d phi. Therefore, this we can write it as m into dr by d phi as it is, m into dr by d phi as it is. And this d phi by dt already just now we have derived. So this we are going to get it as a p phi by m r square. Just before that we have. So how we are getting means, simply we can write what is the value of p phi is. P phi is equals to m r square into d phi by dt. So from this we are writing there here d phi by dt value is equals to p phi by m r square we are writing. Okay, p phi by m r square we have. So now we can write this as PR is equals to p phi by r square 1 we can write into the remaining is dr by d phi. So because mm get cancelled, so we'll get PR is equals to d phi by r square into dr by d phi VR by. Now we'll substituting this value. Now what we'll do is substituting the value of PR. Okay, substituting the value of PR, we get so what actual equation we have is integration. The previous one, if you see here, we have okay integration of PR dr is equals to NRH we have, right? Therefore, here we'll substitute integration of PR value is what we have is P phi by R square into dr by d phi, dr by d phi, which will be equals to into dr, it is there, into dr is equals to NRH we have. Okay. So from this, if you extend this one, so we can write this as P phi by R square. And again here, what we'll do is, here what we have P phi by R square we have written, here we have dr by d phi here. Okay, dr by d phi we have. So therefore, we can write this as this we can write it as dr by d phi, and again we write this dr as dr by d phi into d phi we can write. Okay, so this dr we are writing it as a dr by d phi into d phi we can write. So which is equals to what we have NR H we have NR H. So therefore, to take P phi is outside, because P phi we said that according to the classical mechanics it is constant. If you take outside, the remaining here it will be 1 by R. Next one is dr by d phi, and make it as a whole square. Okay, so which will be into d phi, which will be equals to NR H we have. Okay, so previously we have got this equation P phi is equals to N phi by H into 2 pi, and next we'll write this P phi into this total value is equals to NRH. I make this as equation number 4 here. Okay, so now after this we have to use the polar coordinates here. So using the polar coordinates. So the polar coordinates are r comma phi here. Using the polar coordinates r comma phi. So in ellipse, we have 1 by r value is equals to 1 plus epsilon cos phi by a into 1 minus epsilon whole square. Okay, by using the polar coordinates we can write so we can write this 1 by r is equals to 1 plus epsilon cos phi by a into 1 minus epsilon whole square we can write here. Okay, so here after this we can write what are the things which we have in the previous equation, that is in the equation number 5. So there A is nothing but it is a semi-major axis, because for an ellipse we have a semi-major axis as well as the semi-minor axis. So this A is nothing but semi-major axis we have, and this epsilon or E we can call here this, which we will be calling it as a eccentricity. Eccentricity we can call here eccentricity. So this equation, whichever we have written, like 1 by r is equals to 1 plus epsilon cos phi by a into 1 minus epsilon square. This epsilon is nothing but the eccentricity of the elect, and A is nothing but the semi-major axis we are going to be called here. So now what we'll do is we will differentiate this equation. Okay. So the previous equation, whichever we have, we will be differentiating the above. What is that equation number is? Equation number is 5 we have. So we will differentiate this equation. So if you differentiate this equation, what we have is we will get here as 1 by r square into dr by d phi, which will be equals to epsilon in place differentiation of cos phi is sin phi. So epsilon sin phi by a into 1 minus epsilon whole square. Okay. Epsilon whole square, you are going to make it as equation number 6 here. So now we have got what we call 1 by r is equals to actually 1 plus epsilon cos phi into divided by a into 1 minus epsilon whole square. And this 1 by r square dr by d phi is equals to epsilon sin phi by a minus 1 minus epsilon whole square we have got. Now what we'll do is we will divide this equation 6. This equation 6 with equation 5 we will divide here. So if you divide here, so dividing equation 6 by equation 5 here. So if you divide, what we'll get is 1 by r into dr by d phi. Okay. So which will be equals to epsilon sin phi here we have. Okay. Into 1 is so something is happened here. Maybe some problem here with the net. So it has been disconnected. So once again, I'll share the screen. Something is happening. 1 minute, I'll share the screen once again. One minute here. This is not required. Yes. So whatever we have written previously, it has been erased. This is not okay. Actually, we have to derive this equation. So previous equations has been gone here. So anyhow, so here we write this equations. So from the equations 4 and 5, we have a P5 integration for a surface. We have a epsilon sine phi by 1 plus epsilon cos phi whole square to d phi into d phi, which is actually equals to n r h here. Right. So this we can write it as P5. So this integration is over a limit from 0 to 2 pi we have. So this if we expand, we will get it as epsilon square sine square phi by, you can write it as a 1 plus epsilon or eccentricity E also we can call cos phi whole square, okay, into d phi, which is equals to n r h we have. Okay. So here we will take this E sin phi as some value, which is we can take it as a U, which is E or epsilon sin phi here. Okay. So and V is equals to, we will take it as a 1 by 1 plus epsilon cos phi will be. So if you take U is equals to this and V is equals to this, and we will differentiate these both. So we will get du is equals to epsilon, which is constant. Differentiation of sin phi is cos phi d phi. And similarly, if you differentiate this, dv is equals to, you get it as epsilon sin phi divided by 1 plus epsilon cos phi whole square you get here. So now we have got du value as well as a dv value. So now if you do the differentiation of this one, that by using or we can call it as an integration of u dv is equals to u v minus integration of v du So by using this one, we will substitute the values of all these values like a u value, dv value, all these we will substitute so that we'll get this one next to next one here. So if you substitute here, you'll get it as some p5 into this value is epsilon sine phi divided by 1 plus epsilon cos phi. The limits are from 0 to 2 pi minus integration. This v value is if you take the limits are again 0 to 2 pi, and v value what we have is 1 by 1 plus epsilon cos phi into du value. If we substitute, we can get it as a epsilon cos phi divided by 1 plus epsilon cos phi into d phi here. So which is equals to actually NRH, which we have seen. Right. So now if you do the what we call integration and all those things, we will be getting this value. Next we'll move another. So if you do the differentiation, all those things in this case, we will be getting the final here equation is 1 minus epsilon square. It will be equals to n square pi by n square you'll get n square you'll get here. Okay, and we know that this 1 minus epsilon square actually is equals to b square by a square. B square by a square we have. Okay, so next page. So here if I write continuation. So here we know that 1 minus epsilon square is equal to b square by a square. So therefore, what actually we'll get is b square by a square is equals to what we have n square here. We will get it as b square by a square is equals to n square pi by a square you are going to get. So this we may write as n pi by n is equals to, we can write it as a b by a, we can write b by a we can write. So this condition whichever we have, so this condition n phi by b, n phi by n is equals to b by a whichever we have. So this condition is nothing but the allowed elliptical orbits. Okay, so only allowed elliptical orbits are those for which the ratio of minor to major axis, the ratio of minor to major axis here. So this one, b by a, the ratio of minor to major axis is equals to the ratio of n phi by n we have. N is nothing but the principal quantum number and n phi is nothing but the transverse quantum number. So this is what we have, the allowed elliptical orbits. That means for every atom, we don't have all the orbitals, all elliptical orbits we don't have. We will get so many, but only some of them are allowed by using this condition n5 by n is equals to b by a. So we can get the typical allowed elliptical orbits you are going to get here. So this is what allowed elliptical orbits of the Sommerfeld that we have. And similarly, we can calculate the total energy of the electron in an elliptical orbits corresponding to the quantum numbers n. We can calculate. So if you want to calculate the total energy corresponding to the what we call an electron, the total energy of an electron in an elliptical orbits corresponding to the